First one is AI, second one is security. AI for cyber security. Quantum machine learning, quantum AI, second one is quantum security. একদম কেউ বুঝতেও পারবে না গরুর রচনা বলছি।
Okay, so good morning everyone. We are finally come to end of the course, right? It's a very long and difficult course for you, I know. But there are still some excitement today. We'll learn about this quantum computing, the basics of quantum computing. Okay, so good morning everyone. In today's class, we are going to learn about basics of quantum computing, then quantum machine learning, and then second classes we'll learn about this quantum security, specifically the post-quantum cryptographies and all. So,
Good morning, welcome to the last day, last show. So, first we are going to talk about quantum machine learning or quantum AI, and then we talk about quantum security, and throughout that discussion we will talk about how AI can solve the security problem in the quantum domain. In the last 9 days we basically talked about AI and security in the classical domain. Today we are going to focus on quantum domain. So, what I am going to do, I will introduce quantum computing a little bit, and then we will straight go to the quantum AI and some of the steps that are important in quantum computing, so that you can relate to classical domain, how is it similar or how is it different. So, if you look at quantum computers implemented by different companies, they are using different technology, and the classical computing technology is based on electrical properties 1 or 0, high voltage or low voltage, but this does not follow your classical properties, rather it is basically follow the quantum physics or quantum dynamics. And although it is not shown here, in a month or so time frame, Microsoft came up with the topological quantum computer. That is not classical, that is not quantum, that is some magical phenomena. Those of you want to learn about. So, I am going to talk about qubits, which is the quantum phenomena. This is about anion. So, they are known as anion. If you are interested, they actually build a machine where they can capture that magic and do that reliable computing using topological quantum computers. So, what I want to highlight something. So, throughout this I am basically going to talk about the differences between classical, so that you can relate to it. So, in classical, earlier people are putting 1 or 2 transistors in 1951, now we are putting billions and transistors are getting smaller and smaller. These days we are fabricating with 3 nanometer. So, it is that thin. Here actually if you think the analogy of a transistor, which is qubit, they are getting bigger and bigger and bigger. More we try to put in, instead of making them smaller, they are getting bigger. The reason they are getting bigger, as of today, this is how quantum computers look. So, actual quantum computer is really tiny, what we call as quantum computer. So, you think of a finger, in a tiny finger you have that chip, that is the quantum computer as far as we are concerned. But for the rest of the world who do not know anything, for them to sell something in $100 million, you have to show something, right. This is what we show, and basically it has a lot of wires, and that chip, tiny chip is sitting inside, and all these wires are connected from the quantum computer to all the way to all these devices you see. Those are all classical computer, FPGA and all that stuff. This is actually your quantum computer, although deep inside a tiny chip, that is actually where it is fabricated, and they are going to exploit the quantum phenomena, dynamic physics of the phenomena. It is not the electrical property, it is not the electron flow, then it lost the quantum property, then it would behave like a classical computer. So, normal understanding in the regular world or normal people, quantum is very fast, that is not true. It is just that quantum computer can solve certain class of problems theoretically significantly faster than classical computer. You have seen one of them, or at least heard one of them, like prime factoring. But if you want to do your addition, if you are thinking I want to do my addition faster than quantum computer, classical I can do addition in whatever 1 nanosecond, quantum I will do in no time, 1 picosecond, that is not going to happen. In fact, we do not actually know how to do addition in quantum computer. If you do it, you have to do it thousands of times, you have to measure and you have to hope and pray, maybe once the result would be correct. So, just make sure I dispel that idea. So, I talked about actual quantum computer is really tiny a chip, but everything around it like supercooling, absolutely supercooling temperature you need, and you need all these classical computer to sit there, connect, and to make it work. Now, this is basically the way to visualize the quantum phenomena, although Feynman said do not try explaining any quantum phenomena using any classical example, because that would be 100% wrong, because there is no classical analogy. But today I will try that, and full disclaimer, any comparison I make they are actually wrong. It is just that it makes you kind of feel and understand, instead of showing you lot of equation. I will try not to do any equations at all. So, a cat, this is the Schrodinger's cat, and Schrodinger is kind of assumed as the godfather of this domain. So, Schrodinger basically saying you put a cat inside the box and keep some poison, and that is kind of closed, and then it is intelligently closed. If cat is intelligent, it will be able to open, and if it opens, most likely it is going to drink or spill and going to die. Now, if cat's owner is outside and you ask the cat's owner, did your cat, is your cat dead or alive, that is actually the qubit. You can't say it, because if you are the cat's owner, you are going to think my cat is intelligent. If your cat is intelligent, it is going to be able to spill and drink and die. You do not want your cat to die. So, therefore, you are not going to say that. On the other hand, you can't say my cat is really dumb. I do not think it would be able to open that phenomena. And so this basic idea that when box is closed and soundproof, the ability to tell that whether the cat is alive or dead is not possible. So, then it is probably alive and dead at the same time, 0 and 1 at the same time. That is the analogy of a qubit. A particular computing node in quantum dynamics, a particular thing that is both 0 and 1 at the same time. And little history, and that is what I think I can safely say that nobody understands quantum mechanics. That is the Feynman, and he is assumed to be somebody who can took all the theories and equations that Schrodinger came up with and actually implemented and showed it work, exactly the way Microsoft took 17 years to actually show topological quantum phenomena. It is all nice thing, all these magical things, when they come, either they self destruct or they start dancing, they actually form such a formation, and that actually can be implemented on real device, can be fabricated, and you can measure those, control those. That took 17 years and hundreds of millions of dollars of funding. Anyway, I am going to skip all of that, and what I am going to talk about now, what is the intuition? So, I prepared this intuition for anybody to understand, even somebody from elementary school, but I am going to ask a question. So, you have to understand. So, when you are in a rocket, and the rocket has a position and a velocity, right? And remember, I am taking analogy, those are all wrong. When you have a noise cancelling headphone like Bose headphone, it has a noise cancelling phenomena. How many of you know how noise cancelling works? One hand. So, when you have normal waveforms, normal signals, you have to identify those signals and frequency, and then you have to create signals which is exactly opposite, and then they will cancel each other, right. So, but you have to identify which one is noise. In childhood, when I used to go to the field and doing what they call it, removal of weeds, I had real confusion. The weed and the actual rice plant look exactly the same. I asked my dad, which one should I remove? He said, look at the distribution, which one is more, that is the rice, whichever one is less, that is the weed. It coincidentally that weed is actually rice, it is just that it got mingled. Unlike these days, you go to government shop, they give you a sealed container of the seeds, they are completely refined. Those days it is like everything get mixed. So, it is really one of the rice you call as a weed, another rice you call. So, the biggest problem in noise cancelling is actually identifying which signals are legitimate voice and which signals are noise. So, Amar Bose from MIT was able to do that. Now, if you put this headset on the airplane, that is actually a quantum computer headset on an airplane or the rocket. Assume rocket as a human being, this amount of noise is too much, that is quantum computer. And the key idea here is a quantum computer has a state which can be controlled, and the coefficient states are complex number that can constructively or deconstructively interfere. Remember that noise signal cancels each other. Now, what is happening over the years? The computers we have today we call is noisy intermediate scale computing, everything is really noisy, and in a moment I will explain why are they so noisy. That is why the computing today is not reliable. So, 2023 IBM let me try writing exactly same way, 2023 IBM came up with something like 1023 or some number about 1000 qubit gate. So, that is basically what we have today, and these are kind of noisy. When I talk about quantum error correction, I will revisit it. To make a qubit reliable, you need 4 of them to guard it, 4 or 5 together becomes a logical qubit. If you take any number 127 divided by 5, you are really left with around 20 qubits. With that qubit you can't compute much, but going forward when you have computers with lot of qubits, we will be able to do reliable computing exactly the way you do in classical. We never think of alpha particle hitting and all that stuff, we never worry about it, and that is the problem. But the problem with the classical and quantum is this is a age old puzzle. Even classical domain, because even the day I was doing PhD it is 18 micron technology, now we are talking about 3 nanometer technology. It is already going or seeing the phenomena of quantum dynamics. They are already facing some of these noise and unreliability, all these problems, but very soon it is going to get into the realm of quantum. That is what people are saying. For when it entered the nano regime, people are saying, oh, now it is not going to work, but it is still working, reliably working. When you run a program, you do not worry about it, right. So, quantum computers, when they reach that stage, nobody will talk about it anymore. You will write quantum algorithm, which I will show in a moment. You will run computers, and any questions so far? Now, today even with the quantum kind of story or the unreliability or noisy story, people are still able to solve certain class of problem. Today's lecture I will focus on quantum machine learning. Certain class of problem, quantum communication is very stable and it relies on the idea of entanglement, and we believe in that philosophy in India. Mother and kid has some entanglement. If kid is sick, mother will feel some pain in the chest and all that stuff. Whether that is true or scientifically not, or we do not know, but in quantum domain it is true. You can take 2 qubits, make it entangled, keep one in India, take another to Australia. If you measure, do anything, observe anything on the 1 qubit, you exactly know what is happening to other qubit. Real life, bad analogy. If one of my shoe is right here and it is left, it does not matter where my other shoe is, you actually know that one is a right foot shoe. So, that is kind of the issue of entanglement. How do we create? I will talk about it. But the thing is, in communication, once you entangle and do certain transformation to this qubit, then the information you already get from the other one. And in fact, this is also known as the whole Einstein, Schrodinger, all that paradox. How can something move faster than light? It will take me a semester to explain that phenomena, but just to tell you, it actually does in this particular context. Theoretically, you can leave that qubit from here to let us say Saturn, and you make certain changes here, you are guaranteed that same change will happen there, but let us not get in there. Quantum communication is actually used, at least based on published result. Chinese president uses quantum communication when talking to security people, security apparatus. Quantum sensing is another one. It is basically sensors that do quantum sensing. It has all its advantages. Quantum machine learning, I will zoom in, you will know anyway. In the future, the sky is the limit, because everything is reliable, you can do all that stuff, and it would build on top of quantum error correction. I will talk about little bit of quantum error correction today. Any questions on this space, where we are, what we expect, and what is going to happen? So, head to head comparison. When you talk about today in classical domain, it is either on or switch off. So, that basically is your 0 and 1. In quantum domain, they are 0 and 1 at the same time. Remember Schrodinger's cat analogy? Same time. That means, if you think of a qubit as a tiny dot and you try to measure, You are not going to get, first of all, measuring collapses it, that is a different problem. If you want to know what it is with some probability of 0, it is not written as 0, it is written this way, and some probability of 1, both at the same time. But what is nice property, because we can do alpha square plus beta square equal to 1. Now, it is theoretically possible, at some extreme it is only 0, alpha is 100%, beta is 0, and some probability it could be 1 extreme, but that is like 2 points in an infinite space, you can't just guarantee it. You can try transform, we will talk about it, but and this gives it the power. So, let us observe this phenomena. This is basically every qubit, how we do it, we will talk about it through pulses, but it is both at 0 and 1 at the same time with some composition of them. So, that is basically about the qubits, and then in terms of computing ability. So, this power is not the power, computing power. In classical, you put more transistors, it linearly increases. You have 1 ALU, whatever is the performance, you put 2 ALU or 2 processor, double the performance. Of course, it assumes your program has parallelism, compiler is able to generate parallel thread, you are able to keep those processors busy, all of that is important, but theoretically you can have linear increase. In quantum, it is basically exponential increase. Can you tell me why it is exponential? What did I tell today already that explains you it is in exponential computing ability? Error handling actually is a problem, I will come that later, but why it is exponential? Because recall each of them, so because of 2 reasons, each of them is in 0 and 1 state, that is known as superposition. I will take a incorrect classical analogy, but entangle, so superposition and this whole story of 2 people can be entangled, that is the entanglement. These 2 essentially makes quantum computers so powerful theoretically. Today they are not reliable, that is why you have a problem. Theoretically they makes them powerful, but here is a incorrect classical analogy, because everybody is talking to everybody. So, then if there are n qubits, you have factorial n ways of, so really you have 2 to the power n potential computing ability. So, in quantum domain it is a order of 2 to the power n computing ability, in classical domain it is a order of n computing ability. N transistors, n ALUs, max parallelism of order of n. Here n qubits, because theoretically everybody can talk to everybody. Now, actually they do talk, everybody is talking to everybody, and that actually causes the problem, which is the noise problem. Because if you think about it, if all of you guys are talking to each other and I am also teaching, nobody will listen anything, but here objective is final, whatever is the objective we are trying to achieve, can you achieve that objective? Let us say I said, okay, you guys get together in a group, discuss this and come up with a solution, or whatever you think. Do you want to have a class after the lunch, or you do not want to have a class? If you guys keep talking to each other, nobody will reach any consensus, final objective is not done, right. But this idea of, so one power is entanglement, everybody can talk to everybody. It is a superposition, you may not realize, it is actually super powerful. Somebody is 0 or 1. Here you are saying somebody could be in infinite possible scenarios at the same time. So, the potential state space is huge. So, computing in that space, here to create a state space you have to create a graph of n nodes, n square node, then you are representing. This one naturally represents all these huge state spaces, all these problems. So, it is like a huge FPGA fabric where you can compute anything, and they can all run in parallel. So, that is basically computing ability, and that is actually the danger too. If you tell anybody that I told them classical computer noise is not an issue, they will kill me, because that is their bread and butter for most of them. Basically the people work in the back end in layout, fabrication or post manufacturing, all that reliability issue, and but in quantum it is just too much more, a lot more. So, if you look at the quantum noise, this is nothing. Here you compute once, when do you have to run your same program twice or 3 times? Never, right. Here you really have to run hundred or thousands of times same program, and then you kind of figure out what is the result, because every time it is producing wrong result, at least today. Now, when people say, and which I am going to say, forgive me for saying that quantum machine learning is really interesting and exciting, but what I am not telling you, to use quantum machine learning I have to take classical data, convert into quantum form, that will take a lot of effort. I have to run same computation million, if not million, thousand or hundreds of times, that is taking time. Then I am saying, oh, I am 1000 times faster, right. That is not a great idea, because I am not talking about how much time it take me to do classical to quantum conversion, I am not talking about how many times I am running, I am simply saying one run how faster it is, right. So, there are all these things, when people tell you something, take with a pinch of salt, then things should be fine. The final one is the thing I talked about, that do not try applying quantum computer on anything, on everything that you want to do. I will give you a flavor on what type of problems you should apply, and if you study the theory of computing or quantum computing, there is a quantum polynomial time, a class of problem. Earlier if you studied quantum computer computing complexity earlier, it will not there, but these days you will find another class of problem, quantum polynomial time problem. It is kind of a class of problem. For those problem, quantum computer is wonderful, certain optimizations. Let me take a specific example. Let us say a biology or chemistry company developing an anti-aging cream. For them to do the experiment, they take the particle, and those particle, then they do different experiments and try to figure out whether that would do, if you put it on your skin, would it make you 10 years younger or 20 years younger, right. Now, doing those experiments, those chemical reactions, if you want to do truthfully, it is going to take the age of the universe. So, in classical computer, what people do is actually joke, take the thing, put it on a beaker and put the litmus, if it is green it is great, if it is red it is not good. Like, what? We should put on somebody's skin. They are like, no, we need this approval, that approval, then we need to find a third world country where people have no rights, then we send them there, and 10 years, 20 years we will do. First we do on the experiment, then we do on mouses and guinea pigs, then we will find a third world country, and after that FDA will approve, then it will come on the market. That is why they charge so much premium. Anyway, so here in quantum computer you do not need any of that, you can completely do computation. If you can model skin correct way, if you can model those atomic particle and their reactions, you can accurately compute. Then what is not going to happen, that well, it on experiment it looks fine, but when you put on somebody's skin it just it develop rashes, it is not going to happen. Those optimization problem, analysis, simulations, these do amazingly well. That is why people in chemistry, biology, those simulations, they are the biggest user of quantum computer. In fact, one of the diagram here is incorrect. There is a class of quantum computer, a company called D-Wave. They are building quantum computer of these qubits, but they are not general purpose quantum computer. They are annealing type of quantum computer. The applications that you need simulated annealing or annealing, those quantum computer will do well, and the chemistry, biology, all these people are using the D-Wave kind of quantum computer. Now, if you are a classical designer, then you kind of know how the gates are, what the truth table. In quantum domain people do the same thing. It is just that the gates are, this is Hadamard gate, this is kind of entanglement, and this is the input, zeros and ones, this is the expected output, and there is a notion of truth table, we call it unitary matrix. But the key point is, if you can see, all the numbers look same except there is a imaginary or complex number, that is actually the constructive or destructive interference. So, if you are a classical engineer or quantum engineer, that is basically not much of a difference. And in fact, you do not, if you can call yourself quantum expert if you do just two things. IBM Qiskit, there is a simulator, you can play with it, it comes with a tutorial, and all you have to do know is linear algebra. At the end of the day, if you abstract it out right, it is all about matrix manipulations, then you can call yourself you are the quantum expert. Now, let me introduce the algorithm first, because that is the starting point. And of course, we briefly talked about source factoring algorithm, that if you have 2 prime number multiplied, can you factor it in a very quickly. There is a Grover search algorithm, instead of taking order of n time in an unsorted set, it will take square root of n time, but I am not going to talk about any of them. I am going to talk about one algorithm I developed, not because I developed it, because I want to take you through the steps we took when we did not know anything to coming up with that algorithm. Those algorithms are not famous, but that will give you 2 ideas. If you want to develop a quantum algorithm, what steps you will take and what is this catch, because if you do not know what is quantum polynomial time class of problems, which problem you should try to map to quantum, you will get that idea. And why is it faster? I will give you all the insight, let me walk you through. So, this one is basically a clustering problem, and clustering is needed in everywhere. I do not waste time, I do not have any of these account, Facebook and whatever, in Instagram, whatever crap it is, but even if I do not like, rest of the world does, and when people decide whom to give how much money and all that, who is influencer, right, it all depends on how many people connected to it. So, then identifying these clusters is important in social networks. It is also important in many other domain, even when they are doing brain MRI and trying to figure out is it cancerous or not, they try to find out different kind of protein and whatever composition, that is also clustering problem. Even when Google, you search something in Google and they come up with some list, they also do some kind of page ranking algorithm, that is also based on some clustering. So, given a graph, how do we figure out cluster is a problem that is used everywhere, we looked at it, and the best possible algorithm that was there is spectral clustering. I will not get into what spectral clustering so much, other to say once you have a graph, you do a spectral analysis using the same term to define it, and once you spectral analysis, it gives you bunch of values, either values are here or values are here. It is kind of a simple kind of clustering algorithm in machine learning, that is the spectral clustering. But if you do spectral clustering in your classical computer, it is going to take order of n cube time, where n is the number of nodes in the graph, not even n square, n cube. But if you do in a quantum computer, it is in order of n time. I am going to tell you what is the catch, what is quantum computer doing exactly to reduce from n cube to n. Let me try to show that. How many of you recognize this diagram? This is from your 10+2 book. What does this diagram shows? Yeah, that would do. So, those of you do not recognize it, I do not know whether you opened the book or whether your teacher opened the book when the teacher was studying in their 10+2. But anyway, so this is basically showing that for hydrogen wave function, which roughly speaking, if you recall, every atom has something in the nucleus, electrons rotating around, some are loose, some are tight, there are a lot of orbits, some of them do not like their orbit, they always like the other orbit, they want to move, all this stuff going on, it creates magnetic field, and that magnetic field you can represent, and this specific radius, angular momentum, projection, this is known as eigenvector or wave function. If we can control any of these 2 wave functions, we have a qubit, that is the quantum dynamics. Physics, you take the physics and you implement in quantum computing, that is a qubit. You put lot of qubits, that is your quantum computer. We will talk about how to program them. So, of course, nobody uses hydrogen because controlling this one is actually hard. Microsoft is doing something else, IBM is doing superconducting qubits, some people are doing trapped ion, different people are doing different thing, but that is the key idea. Now, when we looked at it, we kind of figured out that there are 4 stages in basically spectral clustering. One of the stages that take most of the time is computing eigenvalues. So, we wanted to do that. This is the circuit we had to design. When you talk about compilation, it will make more sense. I wanted to show you, if you want to do in a classical computer, how much you have to compute, a lot, and most important part I want to show you, this summation, e to the power and all that stuff is computing eigenvalue in a classical computer. In a quantum computer, you program a qubit, measure it, you get the eigenvalue. You do not have to do all these hundreds or thousands of instruction in a processor, you just set it right, initialize it, read it, done. Why? Because quantum, the computers or these qubits and all that, their natural phenomena is they are eigenvalue by themselves. What all these formation, all these magnetic field, so then that is basically this stuff is essentially they are doing eigenvalue computation. So, that means if you can initialize them right and get the picture, you actually got the eigenvalue, you do not need all these thousands or million lines of instruction. Now, if you want to design another quantum algorithm, see if eigenvalue computation is a core kernel part of it. If eigenvalue computation, which is common part in many analog design and optimization problems, then quantum computing is a perfect fit. Is that the only way to do it? No. I just wanted to walk you through how we realized, oh, eigenvalue computation, that can be done naturally here. We have to set the parameters right, it would orient itself, then you take the orientation, that is the eigenvalue. And if I finish this, you will see what it is we are trying to do. So, we are basically doing eigenvalue computation and those values we are plotting, and either they are in this cluster or in that cluster. So, we still have the initially the graph, you get the matrix, but this computing eigenvalues. So, this eigenvector projection is extra step we have to do, because remember, or I will tell you, you can't measure a qubit. If you, so for example, we have a kid and kid is making lot of noise, but then if you wanted the kid to do something and hold the hand, they are like the most innocent one. Those of you know cats, they always do that. They are the naughtiest one, and then when you come home and they are like the way you are saying, you can't say anything. When you touch any qubit, it would collapse to 0 state. You do not get anything out of it, but it was always noisy, completely 0 and 1 all the time. So, that is basically the algorithm. Any questions? Now, we are going to do the quantum machine learning. So, I am going to solve one specific problem, but before I do that, I want to show you this whole classical and quantum. Classical is one word, quantum is one word. So, there are 4 possible combinations. You are doing classical data and classical computer, you are doing quantum data classical, classical data quantum, and quantum data on quantum computing. Where the data comes from, what type of data it is, who is the computer, 4 possible combinations. And in today's world, when we say quantum machine learning, these 2 categories are kind of treated as quantum machine learning, because this one we are taking quantum data, but still running on classical computer. So, this is not considered anything quantum, just data happens to be from quantum, who cares, right? It is some data, whether it coming from neural network or biological network or quantum computer, you are still doing classical computing, but here computing is quantum, either on classical data or on quantum data, that is known as quantum machine learning. Why is it called quantum machine learning? Wait for few more minutes. So, the way people use today in the world, unreliable world of quantum computer, is something called, people use variational quantum algorithm. The way you want to visualize, you have an algorithm, but there are some parameters that you can tune. If you have a sorting algorithm, think about it again, incorrect classical analogy, think about the in bubble sort, you have 2 loops and the loop bound you can change, but it does not make sense, because the number of things you are trying to sort, loop bound is fixed to that. Let us say it is not fixed for whatever reason, or number of iterations, it is not 2 for loop, let us say you can do n for loops. Some parameters are there that you can tune, and that is guaranteed to improve the performance, and such a algorithm are used in all over the place. I will show example in error correction and compilation, but it is used everywhere, from physics to math to even the machine learning itself. It can use variational quantum algorithm with wide applicability, error tolerance, scalability. So, the way people use today, in a quantum computer you want to compute something, it could be the computing eigenvalues I just said, and then after few seconds, after few iteration, after one shot, you want to read it and give it to the classical computer to see, am I doing right, am I going in the right direction, do I need to change my trajectory. Classical computer will give the feedback, and those parameter, think of these are adder, subtractor, whatever they want to visualize, that is actually not true, then those can be parameterized. So, parameter values will change, it will do computation again, you again look at the trajectory. Ideally, you want to converge in 1 or 2 iteration. Although it is called quantum machine learning, actual machine learning is running on the quantum computer, sorry, classical computer. Quantum computer is doing the computation of whatever algorithm you are asking it to compute, let us say spectral clustering or whatever it is. Classical computer is doing the machine learning. Now, inverse problem exists, that is not popular, people are still publishing because they do not know what they are doing. Remember Feynman said, it is not my statement. So, what they are doing is they are taking machine learning algorithm and saying machine learning is slow, let me use some of the machine learning problems and map it to a quantum computer, let us quantum computer speed the machine learning. Quantum computer cannot reliably even add, subtract, multiply, nothing. What computation will you map? People are mapping, people are publishing, they are getting best paper award. Try not to publish those things. Now, are they useless? We do not know. Maybe many years later when quantum computer would become stable, maybe those problems all would become relevant, all those publications would be great. If this does not become stable, all those are useless. But this one is useful, everybody using it. Do the quantum computer, but the one catch, did anybody find a flaw in this mechanism? Yes, please. Bottleneck of the classical. Very reason we want to start with quantum computer, it is exponentially faster, right. Even the quantum polynomial class of problems. Now, we are slowing it down by the classical computer, not just one, we might have to do multiple iterations. So, but at least for the time being in a noisy quantum regime, this is what is the state of the art. Yes, please.
One question, sir, just to understand this better, these parameters which we use, the weights and biases, is that what the quantum computer is giving back to the classical one?
No. So, this has 4 qubits, right. Oh, one thing I forgot to mention, I should have said, quantum computer is more like FPGA than like a processor. Why do I say FPGA? Literally the way you are seeing it looks like this way, but really this quantum computer all it has is 4 qubits somewhere, that is it, that is all it has. We send electrical pulses which we will show in a moment, then they start dancing in a manner, talk to each other, do not talk to each other. I am forming a gate to say, oh, Hadamard gate, oh, you guys are married from now on, then I apply another gate, now you guys are divorced. So, we are doing this dancing game by sending pulses and those things start behaving like a different gate. This is basically same qubits in time step 0, this could be same qubit in next time step or the 2 qubits later, again they are single. We are measuring each of the qubit at the end of the computation. All you have 4 qubits, that is all your computer in this example. You could have 8, 10, 15, but in this example we are only using 4 qubits. It is more like a reconfigurable computer, you have reconfigurable fabric, you can make them behave in such a way and you over a time frame you send some pulse they behave such a way, send another pulse they transform into something and so on and so forth. It is over a time, this is what is happening to the same 4 qubits, they are transforming themselves into certain behavior. Any questions?
What is the input to the classical computer?
Oh, you had 4 qubits, you measure those 4 qubits, give those measurement values. Yes, please.
What is a qubit?
A qubit is something like remember in classical we had switch on and off, here instead of on and off it is both on and off, partially on, partially off, how much on, how much off, that is basically kind of a qubit here. So, if you think carefully, become little silly, then actually what we just talked is basically a state preparation problem. Let us say you want to do a sorting of 10 numbers, you put bunch of number in your register, run the sorting algorithm, the sorted result in your register. It would be nice if I can initialize those register with the sorted value. I know it sounds silly, if it was sorted, why am I running sorting algorithm in the first place, but really this is a state preparation problem. And that is what I wanted to show you, that if I know the end result I just prepare the state, and in quantum computer you can actually do, and I will we developed a very interesting idea for that, I will talk to you in a moment. But essentially all the final result I am not talking about, I am talking about when this machine learning tool figured out something, how parameter need to be initialized, think of those values are coming, you are initializing those parameters or those registers, that is basically the state preparation problem. And then you measure and those measurement you give it to the classical computer. Any questions? So, most people work, when they say quantum computing they are working here, Two other problem most people do not work, then who works those areas? That is me. State preparation and quantum measurement, and both are important. I will try to give you that flavor. Do not get into the crowded territory where people are working, try to work on the areas where people are not working. All three of them are important. If you do not prepare the state correctly, it is like you are not preparing a state in a classical computer and you run something, what is going to happen? Garbage in, garbage out. You initialize state properly like program counter with the start instruction, then you compute, it will produce something. Same thing, your measurement is flawed. So, Rigetti Computing, another company like IBM and all. So, they came up with how do we do this eigenvalue solver using kind of quantum processor and classical processor. This one is running machine learning, this has a technical term, it is basically computing ansatz, and this one is basically preparing quantum state. That is where I got the idea that this computation problem can be viewed as a state preparation problem. You prepare the state again and again and again, you measure the term, you compute it. That is actually eigenvalue solving using quantum machine learning. Now, what is state? How do we prepare state, right? So, first question we wanted to answer ourselves when we solve this problem, how people are preparing state today. Even before I became a faculty, quantum computers are there in small scale. So, how are they preparing state? Do you have any idea? No, you prepare the state. If I am angry, what do you want to do with me? Like most of you are not answering my question. If I get angry, what do you want to do? You take me, open that door, put me there, close the door from the outside, and you hope I will eventually cool down. That is what people do. In a very cold frigid environment, do not do that to me, very cold frigid environment, you basically let the qubit cool down. Why did they got excited? They are talking and all that, does not matter. You put them in that frigid environment, and then you kind of know they are prepared to the state. Two problem, you put me in there, and then how do you know when I am going to cool down? If you try open once in a while, if I am so angry I might punch at you. So, there is a risk associated there, but that is also a solution I will come to. This is known as passive reset, you just let it cool down, but only downside is the state preparation problem may not be prepared only to 0 state, because passive reset takes you to the 0 state, and the time it takes depend on how many people around you are excited, how many people are crying around you. That would mean how long you will keep crying or you will be angry. You might be trying to cool down, other people are angry, you should be angry, this is injustice, intolerable. If all the qubits are doing that around you, too many of them, lot of entanglement, then it is going to take a long time to cool down. So, the time is an issue, and also it can only take you to the 0 state, then you have to apply some gate to go to the target state, whatever state you are trying to prepare. What is this state? This is the state that classical machine learning decided what your parameters should be initialized with. Now, then people say, well, this opening the door once in a while to see how I am doing, how angry I am, that is the kind of active reset. You kind of let it cool down, then you measure, and a classical computer kind of checks, yeah, it's cooled down enough, I need to wait few more minutes, like opening door once in a while. What is the problem with active reset? The good part of active reset is you do not wait like indefinitely for this one, you just check. But what is the problem with this one?
You are stimulating it again.
No, you are involving classical computer again. All the speed up you have, first we give up, because classical and state preparation, even within state preparation itself we are involving classical computer again. The slowdown of classical computer is again getting involved. So, what we came up with an idea, I do not think it exists these days. If somebody want to teach their daughter-in-law a lesson, what mother-in-laws do? They beat up their daughter. This used to be the case in 30-40 years ago. So, I thought that is a great idea. Let's if you have 2 qubits, this is the system qubit, I want to initialize, then let us entangle with another qubit, we call it a auxiliary qubit, and let us keep harassing it. Remember the beating it? The harassment is we keep measuring it, and interesting phenomena, actually it all exists in the community, in the physics community. everybody knows about it, anybody in physics. We are the first one to show this will actually work on physical quantum computer, that the simple act of harassment will drive this qubit to the target state. You know the magic, there is no classic analogy. I did not even tell anybody which state I want to go, but it will go to the state. Arbitrary state initialization, we call it arbitrary state initialization using quantum steering. So, in physics domain, developing a theory is powerful and showing it actually work is equally powerful, maybe more powerful. Remember the topological quantum computer, it existed for eternity. It took hundreds of millions of dollars, maybe more, and 17 years for Microsoft to actually show, and it just happened only few months ago to show it actually works. So, it is not a trivial thing, but either way we came up with this idea of quantum steering, how it would work and what are the limitations, and we kind of worked on extensively on this. Any idea of quantum machine learning, specifically on quantum steering, before I zoom in? Right. So, and basically just to show that you can initialize qubit, these are different IBM quantum computers, but I want to just tell you that there are two ways you can start doing quantum experiments. IBM has a nice tutorial on Qiskit, let me write it out. IBM Qiskit, and you can play with that. It is basically a quantum computer in a simulator environment. If you really want to do real quantum computer, up to 5, 7 or very small number of qubits, it is free. You have to create an account in IBM cloud, and then you have to submit your job, the quantum circuit. I will show you how circuit looks, how do you prepare, how do you compile, you submit it, and then it would process, give you the result. Now, whether actually it ran in the IBM quantum computer or some classical computer ran and send it to you, that also I will talk. How do you know? Yes, please.
Yeah, so you said to check whether it's cool or not, we have to check it. So can we measure the number of qubits which are like acting in weird ways, and then can have a formula to just detect the time how much it will take to cool?
Absolutely, that is how it is done actually. So, every qubit when they are in excited state, they are not in equally excited states. So, you are still measuring, I am only talking about one qubit, but the problem domain you opened up, you are talking about multiple of them. That is a lot more complicated, because everybody will not cool down at the same rate. Some people will stay angry for a long time, somebody becomes very angry, short tempered people very sharp, but then slow down quickly. So, there are a lot of such phenomena. The qubit, even the qubit placement also make a scenario. So, let us say these are the qubit towards the boundary, they will cool down much faster than the qubits that towards the middle, because they are getting they are hot, and other heat or other anger or other whatever excitement, that is also not helping them to cool down. So, that is also true. Now, so active steering, as I said, you open the door and check, and then eventually you might change the unitary how to cool down. So, once you just say cool down, other time you might pat, and whatever it is, it might change active steering. So, we also worked actively on active steering problem. But now I want to show you something more interesting, which actually we saw some result interesting, but or we expected good result and we are not getting good result to publish. And then we sometimes when you do research, you have a hunch we are doing a great work, but your results are not better than the state of the art. Then you kind of see, what did I do wrong? So, for doing that, let me straight take you to the, instead of explaining any of this stuff, let me straight take you to the results. So, here is a hydrogen ground state energy we are computing using passive steering. So, think of in your quantum computer, you build a circuit, you are computing, let us say ground state value, or you are doing eigenvalue computation of an atom. So, you model that atom or that behavior based on qubits. Now, you are measuring, when after the computation is done, the ground value it provided, did it match the mathematical exact one. I think this is, we done this using NumPy solver in Python library, that is what software gives you. Now, then what our problem was, then we are using existing Qiskit. Qiskit has some library to compute it. We are using Qiskit, that blue line, and you see blue line is also there and our work is also right there. So, we are getting the number of exact mathematical computation, so is the state of the art. So, we kind of felt, oh man, all these work went nowhere. Then we observed, we had to zoom in and understand what is this Qiskit algorithm, and it took us kind of time to figure out that Qiskit have an assumption that you have to tell where to start. So, for example, if we want to come to the CET building, our objective is to come to the CET building, but Qiskit is assuming tell me the front gate of IIT Guwahati, put me in IIT Guwahati front gate, then I can go. So, we did not realize that Qiskit is making that assumption. Now, I know it is silly, you want to prepare a state for somebody and that state preparation says, oh, you need to put me in IIT Guwahati front gate, but that is also a state preparation problem. To do that you have to do something, but it is just that there is a research called Hartree fork, at least for eigenvalue computation. Once you call that function, that is trivial, putting in front of the IIT Guwahati entrance, that is actually easy, but then it needs to travel to kind of or find out the qubit should find a mechanism to travel to the arbitrary state where it needs to reach, right. So, once we remove this and say no, that is unfair, our system is starting with arbitrary state, a random state, you should start also with the random state. If we make Qiskit start on a random state, it is not giving good result. So, then we became happy. So, I know this is not interesting, you are solving a problem and your solution is not right. So, then we have to find out how can you make solution right. Whatever it is, the key idea here is I wanted to explain to you that it may seem lot of things may seem unreal, but that is true in quantum domain, that you can initialize to a known state without even doing quantum computing, but going from there to somewhere that you need to do quantum computing and so on to reach to a state. Now that I am done with the kind of quantum machine learning, I want to take you through little bit, at least let me talk about quantum compilation problem to put everything in perspective. We talked about quantum algorithm, whether it is Grover search, whether the spectral clustering developed by us or source factoring algorithm, you may have some constraints. We use a language called Rust, you can use whatever your favorite language, you can use Python, but the typical synthesis problem there are many, but these two are widely used. If you want the heuristic algorithm, cosine sine decomposition, you want kind of close to optimal, that Solovay-Kitaeb algorithm. Once you do, it is going to produce a quantum circuit. Analogy, you start with a C system C whatever program, and then you get an assembly or you get RTL or get level netlist. Once you have a get level netlist, then we do layout. Oh, actually no, let us do FPGA. So, this should be your let us say this is system C, that analogy will work. System C, this is your RTL or let us say Verilog code, this is your Verilog code, and this would be equivalent to bit streams. If you recall, we are generating bunch of zeros and ones and feeding it to the FPGA, that would be the closest analogy. What is happening? You have the specification of the algorithm, then you have the quantum circuit, then that circuit, now remember we are using the quantum computer through cloud, or you can use directly on the Qiskit simulator, whichever it is, they take exact same input, and those are electrical pulses. I will show you that in a moment, those are electrical pulses. Anybody has a question on this full flow? These are basically, go ahead please. These are basically electrical pulses, the pulses that would be given to the qubit. Yes please.
My question was about electrical pulses.
I will show you the pulses in a moment. Anybody else have any questions? Okay, so basically to generate the pulses, I know I want to initialize a qubit to something. How do I make that happen? So basically the algorithm called grapes are sour, it basically computes that if I start with a random electrical pulse, what happens? Of course, in a simulation model, what happens, and then tries to minimize that cost function. Think of again machine learning, minimize that cost function, and wherever it is minimized, that is the pulse it produces. I am going to show you an exact animation. Before that, I want to introduce a quantum gate called C0 gate. It has a funny behavior, let us not try explaining why it does that. You have two inputs x and y, I put 0 0 0 1 1 0 1 1, and then if x is 1, then y will flip. So, this is y plus x phenomena. So, if x is 1, then it was 0, it will become 1, and here x is 1, this was 1, this will become 0. That is basically the phenomena. If you put in a truth table, this is what it's supposed to be, and as you see quantum gate, if you take a picture, this is what the state situation be, but what it should have happened, this should have been yellow, this should have been yellow. Oh, it is already started, let me go back. So, what needs to happen is these pulses will generate, and when pulses generate, you will see the transformation happens in the qubit. Of course, we are measuring the qubit, knowing what is happening, and eventually if it is working correctly, most of the time it does not, then it should match exactly the expected behavior. Those areas would be have 1 or whatever you want to look at it, high values, other areas should have low. I just wanted to give a pictorial illustration, and you realize this is also technically incorrect. I am taking a classical analogy, but pulses are exactly electrical pulses. You need to find pulses with certain amplitude and certain duration you need to apply, and you have to keep trying it. The reason we have to try, and remember you Om had a question that how do we kind of get to that. If each qubit is actually reliable, then you can mathematically compute and produce the pulses. We have to do all this stuff because qubits are unreliable, and in fact they are so unreliable, every day IBM decides which of the qubits to release. 127 qubit, I do not think they will give it for free, only if you pay, and its payment is like every minute $1000, it is very expensive. If you pay, then they will let you use, even then you will not find 127, 5 or 10 of them will not work. That morning they did not get up on the right side of the bed, and they did not have tea, whatever it is, they are in no mood. So, at the morning the IBM engineers will try to characterize them, we call it characterization. Are they behaving the way they are supposed to behave? If some of them start behaving in a very weird way, then they will be blocked that day for performing any activities. They will not be make available to public. I do not know how they quarantine, what they do, but to skip all of that, if you want to do quantum compilation problem, lot of optimization we kind of published, how do you optimize them, and as you can see every place you have a machine learning using auto encoder in machine learning, you can kind of do that. So, let us have break. After the break we will talk about different solutions including quantum security. Thank you. At least Om is asking some questions from elementary school. Look, even if he is not understanding, I do not mind. These guys should ask questions. I intentionally got him to make you guys angry, to show you guys something. Whoever I found on the street, I asked him to come. It just so happened he got 99% today. Actually, he got 100% on everything, only one subject he got 99, and that happens to be Hindi. Thank you. Let us have tea, and we assemble at 11:30 here.
Okay, so welcome back again. So today's plan you are all aware, right? We'll have 1 more hour from sir, and then we have a good lunch, and then from 1:30 to is a half an hour exam, MCQ 25 question. It should take 5 minutes. So you give the exam, and then Ishwar and other will check and try to get the marks. But only thing is that what I understand, the grade card, we need our dean's signature, not my signature will work there, because it's a 2 credit which you can transfer to your course curriculum, right? So and it's a official grade card will be given from IIT Guwahati, not by me. Okay, so only thing is that who are giving exam today will not give you the mark sheet or the grade card today, which will send you over by a scan copy by next week. Okay, so because it has to go to academic section, they will scrutinize all those process and something like this. It cannot be done in 1 hour. Okay, but we'll send you. Ishwar will send you. And 1:30 to 2 is kind of this. Then we'll basically I want to next 1 hour I want to use to learn from you what was our expectation coming here, and then how much you achieved here, whether me or Prabhat sir actually met the expectation of you, and any other comments, anything, right? And then we'll have a small function where we try to give you certificates, some mementos and all those things. Okay, so by 3 we should conclude today. Okay, thank you.
Good morning. In the previous lecture, we talked about quantum machine learning, and now we are going to look at how different other components during the quantum machine learning process affects each other. So, if you recall, we talked about quantum computing has 3 major phases. One is state preparation, one is quantum computing, another is measurement. Measurement is also very noisy, as I talked about. I wanted to show you how you can use machine learning in the quantum measurement process also. So, how is quantum measurement done today? So, basically different qubits when you look at from a quantum circuit, the measurement device will find those values, and you are running same experiments many times. So, you are going to use machine learning tool. In the community they are known as a discriminator. I did not come up with that name. So, then discriminator tries to figure out what is most likely based on the probability distribution, what is most likely this value is. So, n classifications or n machine learning is needed. Instead, what we are kind of proposed that because these qubits are coming related to the same circuit, so if we can use some kind of statistical learning, then one machine learning call would be enough. So, our objective or hypothesis was 2 things. Machine learning does not give you any guarantee, sure 98-99%, statistical learning gives you guarantees, that is one. Second thing is, these qubits whatever computations they are doing, they are not independent really, they are kind of related. If they are not independent, why are they using separate machine learning to find out what those values are? And it turned out our hypothesis is right. In a classical one, when you in a traditional or existing quantum measurement, you get like blobs of these values. What are these blobs? The different distribution of zeros and ones. Every qubit could be a mix of zeros and ones, and you are trying to figure out is it 0 or is it 1, and then you kind of try to figure that out. What we are saying, instead of treating them individually, try to come up with a function that kind of captures, that is typically known as distribution based classification or cumulative distribution function in statistics. And then 2 things it happens. So, the existing approaches are expensive, you have to do many of them and low accuracy. This one you will get high accuracy with few measurements. Our objective is to try only once did not work, but that is basically the objective. I want to touch upon quantum error correction just to show you how it is different from classical error correction. So, quantum circuits being noisy or qubits being unreliable, error correction is kind of an absolute necessity. In layman terms, when you want to initialize a qubit to a specific combination of 0 and 1 with specific value of alpha and beta, it is not going to be that way. In fact, quantum error correction is during runtime. So, lot of qubits are working, some of the qubits might be doing fine, some of them may not feel like working that day. So, during runtime the quantum error correction mechanism need to detect which qubits are not doing well or health is not good and provide sufficient reparation for them, so that other qubits do not get hampered and they keep computing. So, that is basically the difficulty, but two major point is in classical you can measure a bit and figure out it is wrong, like error correcting code, and you can fix that, change that. Here measurement is not allowed, measurement collapses the state. You try measuring anybody, it is going to show you 0 value, that is of no use. That does not mean it is actually 0, it might have been correct, you just do not know. Second thing is information cannot be copied, you cannot copy information. That would have been nice, we kind of kept a shadow like the way classical we do, we keep a shadow register, they keep continuing, if branch misprediction happen, we come back, copy back shadow register and continue from there. Copying is not allowed, you are going to get a 0. So, that is why there are a lot of solutions. One of the error correcting code that works popularly is called surface code. It is just coincidentally surface code idea actually came from topological quantum computing. This whole dancing of qubits, how they help each other without getting into the details and theory. Layman terms, if you want to think about, if this is the qubit you want to protect, you put another 4 around it. So, in a classical analogy which is absolutely wrong, when this one loses energy, momentum, these will gain and they somehow 4 or 5 together maintains the story. So, that is why from a user perspective, if you do not want to deal with error correction, then if you have 100 qubits, assume you have 20 qubits. Every 5 physical qubit would be considered as one reliable logical qubit. But error correction techniques have lot of initial problems, like how do you prepare states. Remember, this is not a classical domain, number 1, and surface code works on the topological world, and you might want to study little bit of topological quantum computing, and you would be amazed if quantum dynamics or qubits amazed you, topology will amaze you even more. It really will seem like magic, really such phenomena happen in particles, it does, and mathematicians and physicists know it for generations, but only Microsoft is able to produce it. The final one I want to talk about is quantum verification, and I want to introduce you to a researcher. Remember earlier in the side channel I introduced, if you want to be a researcher like work like Paul Cocker, publish 5 papers in your whole life, whole world will do it. So, Dr. Urmila Mahadev, she worked in a PhD problem, and problem is interesting. How do you know quantum computer is actually doing quantum computing? It took me 6 months to read her thesis. You might want to read her thesis, you might not want, but the point I want to highlight, if you want to do research, solve a problem, be like her, not like me. Solve one problem, rest of the world would get mesmerized, one problem. And this problem is very important in quantum verification. If quantum computer does not do quantum computing, then all this hullabaloo is gone, all theoretical guarantees, exponential speed up, everything is gone. There are many, rest of the world is solving tiny corollary problem. If I send a request through IBM cloud and IBM says here is the result, how do you know it actually ran on a quantum computer? Because going through cloud, being in the queue, that takes minutes, hour, if not days, and a classical computer can run it. And anyway, most of the problems you will be solving 4 qubit, 5 qubit problem, even up to 20, 30 qubit problem can be solved using classical computer. Quantum simulation of 20, 30 qubit is possible, 2 to the power 30, 2 to the power 20 is possible. How do you know? But this research problem is much more complex than that. You might want to read and spend 3 to 6 months understanding what she has done. But there are, if you do not want to deal with that problem, if you want to deal with sillier problem, then you want to do in like classical world, if you have 2 sets of circuit, one may be very high level description of the algorithm, one kind of synthesized version it, how do you know they are equivalent? different transformation you did. If you recall, when I talked about quantum compilation, you start with C like code, Rust code, then you get a quantum circuit, then you get pulses, electrical pulses like your C code, your assembly, then your binary. How do you know this compilation was correct, and you can do equivalence checking and all of formal verification I talked about. People are publishing in those area, mostly Robert Willi from Technical University of Munich actually published tons of ideas in this space. We worked on also quantum assertions, how do you do monitoring in the quantum circuit itself, and then few other problems we introduced and we felt it is kind of important, which is most people, as I said, when they say quantum computing, they focus on the computing itself. There is nothing wrong. In classical world, that is pretty much it. But in quantum world, you have to do state preparation. Remember quantum machine learning? The machine learning tool is initialize in iteration. So, state preparation is important, and then also measurement is important. So, if you create benchmarks where the benchmark is also only measuring your computing efficiency, that is not a great idea. So, therefore, we developed benchmarks that actually takes care of state preparation, computing and measurement itself. And as I said, in quantum error correction, the computing itself has measurement and state preparation and computing also. So, the benchmark should be reflective of all the components of quantum computing. Then the last idea I want to introduce, quantum verification problem. So, remember classical we did the thing, we thought why can't we do this one. First of all, quantum computer is in IBM TJ Watson Research Center, we won't have access to that. Through cloud we use it, and even if we get some result, even if you work in IBM TJ Watson Research Center, I do not think they will allow you to get into that super freezing room and touch the computer or probe into something. You still have to deal it from the outside. You run it, you get the data. So, the way we run through cloud, they probably also run through similar thing internally. So, the question is, if anything goes wrong, what do we do? Almost a decade I spent on how do you debug when things are fabricated, the trace signal selection, all the ideas I developed, the company implements them now. So, I thought quantum domain, let us start something. So, what we kind of see in quantum world, if you say, people will say, oh, those solutions exist, they call it quantum process tomography. For a normal engineer, they said, I have no idea what are you talking about. I ran 2 plus 3, I did not get 5, tell me what to do. You can't tell me, oh yeah, some variation happening, something happening, process tomography we call it, or characterization we call it, does not matter. What we say, we wanted to break it to engineer terms. Let us say this particular is actually the quantum computer, this is actually real quantum computer, and this is actually a simulator, a simulatable model that is parameterizable. We apply a input and we measure, we get some data, and then what we want to make sure, let us say we got a 4 here, actually it should have been 5. Then the question is, what probably went wrong here? Let us say I passed 2 and plus 3, you and I know nobody uses quantum computer to do addition, it is just an illustration. What went wrong inside? It is producing 4 instead of 5. So, the way, if it is classical world, we call it mutation testing. So, let us say inside there is x equal to, if a greater than b, then you do x equal to y plus z or something like that. The mutation testing said, try mutating some of the operator, try changing this greater than to less than, this plus to multiply, maybe one at a time, and see if we can produce 4. If we can produce 4, then we know that is probably what happened. But the problem is, given a program, there would be so many ways you can change to produce 4, you do not know what it is. So, that is what bothered us first. It turned out in quantum computer that probability is low. You will have 1 or 2 solutions that would produce the incorrect result, assuming it is a noise free. If it is noisy, that is another worse problem to start with. So, we mapped it to the machine learning problem, there is a lot of buzzword, just ignore it. Basically, we are trying to figure out, we are trying to modify this model with parameters such that the difference between this output and this output we can minimize. So, this is basically loss minimization problem based on gradient descent, you have remember that from the machine learning, we call it Riemannian gradient descent, and we kind of solve a lot of interesting problems in that. How do you operate on the Riemannian manifold, and how do you know the solutions you get, and solving all that problem is very interesting. And coincidentally, topological quantum computing also works on Riemannian manifold. It just is, everything is a small world actually, but either way then you kind of update this parameter until it produces 4, then it is a loss function, and realizing that the number of solutions possible, changes possible to make it 4 is very small, 1 or 2, then you kind of know that is exactly the problem happened there. So, that is pretty much kind of brings me to the first set of lectures. So, in the next lecture I am going to talk about quantum security. Yes, please.
Sir, we are talking about quantum measurement. So we are measuring the velocity and the state of qubits, or we are measuring the quantum efficiency?
Those are just analogy. There is no state, no velocity, nothing. It is basically alpha and beta, that is all we are measuring.
Okay.
Alpha 0 plus beta 1. When I say I measured a qubit, all I measured alpha and beta values, or all I am trying to figure out how, what. You remember, you cannot touch a probe and measure it. There are intricate mechanism. I didn't get into, I wanted to abstract that out. Alpha and beta for each qubit, that is what we are measuring.
Okay. And the second question is like that, is there any way to measure or observe the quantum system without disturbing it? Because the scene we are measuring the system, it collapses.
Right. So, that is exactly how measurement apparatus is built in. It is kind of a coupling it creates. So, that measurement apparatus is actually classical. It creates a coupling, some form of entanglement, and then so the information get transferred, the measurement equipment is actually not touching the qubit, and it is complicated because if qubit is in the boundary, that you can visualize, okay, there is something, some magnetic resonance, something EM it is going to do, but if qubits are inside in the fabric, it is kind of complicated. That is why you put more and more qubits, the qubit size bigger and bigger, and the chip size is becoming bigger and bigger, because you have to put the probe all the way, all these big wires, big measurement device goes all the way. In fact, that was the hardest problem in topological quantum computer, that how do you kind of, one is how do you create those phenomena that anyons are dancing or distracting each other, either they dance or they kill each other, that is 0 and 1 coincidentally. Question is how do you actually measure it, whether they are dancing or they are in, and so finding that phenomena, that measurement apparatus, that was the most expensive there. So, this is also expensive phenomena. Yes, yes sir.
What is alpha and beta?
Oh, alpha and beta is, so remember in each qubit, it could be, in each bit in classical computer is 0 or 1, switch on or switch off, but in quantum it could be 0 and 1 at the same time. It is like you are hungry and you are not hungry at this, you are confused state. So, then that is the probability of I want to eat and the probability of I think I am hungry, not hungry, that is basically the alpha and beta, and where the relationship is alpha square plus beta square equal to 1. Okay. All right. So, now we are going to move on to the last phase. Let me begin it fresh.
One more question.
Yes, please.
Sir, you told
More questions you ask, biryani would be delayed. Go ahead. Go ahead.
That is better actually.
Okay.
So you are telling us that quantum computer is answering all the possible ways. So how we know if this is the right answer?
Okay, yeah, that is what Om asked me, that this currently it only works when you know what is the expected value. That is why you keep running and doing probability, because right now things are very unreliable. So, you have to know what you are expecting. So, it is the same analogy as in training machine learning. Again, I am not supposed to take analogy. When you are training the machine learning, you kind of know which one is right, which one is wrong. You want to train it to get 100% accurate classification. At that point, you can rely on it and use it in the real world. So, what we are talking all this right now is the infancy, because I made my hands dirty, played with this quantum computer. If you are attending any other talk, they will assume quantum computer is completely reliable. You do not have to deal with anything. Whatever you develop, you will get that quantum speed up, whatever quantum supremacy speed up, whatever you are supposed to get. Okay, let us begin the recording, please. Good morning. Welcome to the last lecture. In the last lecture, we are going to talk about quantum security problem, and earlier we talked about quantum machine learning. So, I am basically going to talk about mostly, because the way quantum computer is used today, it used in conjunction with classical and quantum, the machine learning I talked about. So, I am going to look into that, their interactions. Mostly I am going to talk about the key idea of post quantum cryptography, and then if time permits I am going to conclude with some applications of security and interesting trade offs. So, when we talk about classical quantum computing today, you are going to submit your project through or circuit through the cloud, and this is you and I, and this is where actual quantum computers somewhere, depending on which company's quantum computer you are using. It depends whether Rigetti, IBM and Google and Microsoft quantum computers are not available, but there are many other parties online. So, this is basically the classical side, this is quantum side. While your quantum circuit is going through, the same classical attacks are still possible, and while the quantum computer is doing some computing, I will talk about what kind of security problems are happening, and there might be security problems at the intersection of those. So, let us talk about the classical one, and this would be kind of a recap what we did earlier, but I wanted to just highlight only story changes is the information that is, this is more like a cloud security problem, but we are going to look at all of them, and we are interested in the quantum circuit that we are pushing through, that quantum circuit security while it is transit. In the classical domain you might talk about your program, normal data and all that stuff. So, somebody might through side channel do different things, and we talked about power, talked about electromagnetic emanation, we talked about the timing attack, those are still possible to get somebody your the quantum circuit that you are pushing through. And also the different types of integrity violation is possible, whether it is a fault injection, clock fault injection, EM, laser fault injection, different type of integrity violations are also possible when you are sending through the circuit. In the of course, the assumption is attacker has access to some of the cloud computing servers indirectly or indirectly. And then this problem was the favorite one we talked about when we talked about RSA algorithm. If you recall, we talked about one of the key step in the RSA problem, at least in key generation, the idea that you generate an intermediate value of n by multiplying 2 prime number, that can be done fast, but if somebody I give the n, finding this is basically the hard problem. Until around in 1990s, Peter Shor came back and said here is a quantum algorithm which can do this prime factoring in almost no time, with the assumption that quantum computer is reliable and stable, which is not today. So, whatever it is, that is basically factoring, it is essentially coincidentally Professor Shah, going back to your thing, it actually uses quantum Fourier transform at the core of the solution. But whatever it is, so that basically started all these flurry of scare, and that started the domain of post quantum cryptography. I will give a glimpse of it very high level, but the key idea of post quantum cryptography, I wanted to just say post quantum cryptography has nothing to do with quantum computing. It is simply the fact it is still a classical cryptographic algorithm, it so that it was designed or selected in such a way, so that if tomorrow quantum computers are powerful, reliable, they will not be able to break it. That is the only quantum connection, but all of it is classical. The name is post quantum cryptography, it is classical cryptography in the post quantum era. Even if there are quantum computers, it will not be able to break it. In layman terms, in RSA, it is basically you are dealing with prime numbers or prime multiplication. Then people thought those are weak, they moved to elliptic curve to make it even. These are taking normal integers, elliptic curve takes only the points on the elliptic curve, additional level of complexity, and in the post quantum cryptography is really it is a lattice based cryptography. So, it is I will not say exponentially, but significantly more complex than the previous one, right. So, now I just want to give you a timeline idea what actually happened in, although Peter Shor did it in 1990s, people take lot of time to digest it, government took lot of time to adjust and get billions of dollars, different countries, and actual competition started into the initial call was in 2016. So, there are 69 submissions, 69 possible cryptographic algorithms, and 2019 from 69 NIST selected actually 26 of them, and then finally 2020 there are 7 third finalists with 8 alternates, and finally 2022 about 4 was accepted, and most people do research on these two, crystal Kyber and crystals dilithium. These two most people do. So, there are I believe 2 encryption and 2 digital signatures, there are 4 of them, but whatever it is, this is basically the standard today in most of the world. When they talk about our security algorithms are post quantum resistant, they basically use these algorithms. And as I said, even the day it was announced 2022, just few months before, some folks published that even these algorithms can be broken by side channel attack. So, of course, it was not designed for side channel resilient, in fact, it did not even have side channel mitigation in them. Once you put mitigation, maybe it will work, but nonetheless they are side channel resilient. And kind of just to instead of showing what those algorithms does, I wanted to show you why the side channel community was so successful, because the day it all started 2016, people started attacking all the stuff, and the people who were able to demonstrate here, they were already breaking things, and I just want to give a glimpse of that. Oh, before I do that, so all these kind of security algorithm, if you kind of see for different kind of categories, this is digital sign and authentication, public key encryption. So, different algorithms are in different categories, when initially all of those are there and then some of them got selected. But what I want to show you, this side channel attacks, oh of course, this we already know how this attack happens, but in the crystal Kyber, one of the ones that I said there are 2, dilithium and Kyber, and crystal Kyber, if you look at the attack, they are basically doing effective message recovery attack by deep learning based power era. Remember, these are classical cryptographic algorithm. So, all the classical side channel attack works on them. This is like normal algorithms, right. So, then message recovery attack happened, and then there are many variations, sliced multi-bit error injection technique, effective message recovery, valid cipher text, recovering the session key, and then people are doing attack on multiplication algorithm. All of that, the previous slide I said, they based on different type of multiplication algorithm, and people kind of figure out how to break those multiplication algorithms. So, people are not trying to break the theoretical guarantee of the algorithm. People are trying to break the components it used to build the theoretical guarantees. Can I break some of the components? In fact, if you remember elliptic curve cryptography, before Montgomery multiplier was introduced, the original multiplier people just broke the, I think the almost at same day or within a month of elliptic curve cryptography was introduced or accepted as a standard, somebody broke it by breaking the multiplier, and that then they changed it to Montgomery multiplier, and that happens to be resistance to those type of attack. Here the first thing they went for multiplication algorithm, and then there are also different variation point wise multiplication as threshold level, secret parameters in the scalar multiplications, and different parameters they are able to break. So, then CPA, what is it? Correlation power analysis. So, that attack retrieve the secret key, and there are variations, divide and conquer strategy instead of doing brute force, and then again from the multiplication and entity coefficients with only 200 traces. So, side channel community, one of the interesting factor is how quickly can you do it. Even in obfuscation, when Professor Karfa talked about it, when you say something is really strong, then you say how long the SAT attack will take to break it. If it is long enough, then you call it okay, reasonably secure, right. Same thing for side channel attack. If you need millions or billions of traces, of course, then you have to say how long does it take for me to get that traces and analyze it. If it is months and years, then people will say, well, that is reliable enough. So, 200 traces basically I can do it in no time. Then attack on message encoding functions, there are many variations. I am not going to go through laundry list, except to say if you want to start in this domain, you are already behind by at least a decade on the side channel attack on cryptographic algorithms. People started in early 2010 almost, right. So, that is about on Kyber, and you should not be surprised, same thing for dilithium. Let us see how I started here. Oh, the animation goes in a wrong way. So, basically all of those, so in PQC algorithms, Kyber, Saber, NTRU, and many of these algorithms, electromagnetic side channel attack actually works reasonably well, and they are able to say secret key extraction. And then there somebody came up with a masked implementation of Saber algorithm, and people are able to do deep learning based power analysis and able to successfully get the key. Then this NTRU, that multiplier leakage of, so basically leakage of the target processor, private key recovery, single trace. Oh, this is actually one of the interesting work. One trace will be able to break the key just using one trace. So that's actually interesting idea. So there are a lot of work happened in post quantum cryptography space, but most of the attack, I don't know, I haven't seen any attack where people actually broke it mathematically or the logic or any flaw. I didn't see that, but all the break are on the side channel space. So there are a lot of countermeasures, people looked at it, and those countermeasures happens to be that you have already studied or looked at. So masking is one of them, but it's not quite effective, as you can tell. And then there are some solution. So basically people are then trying to do, can I do some kind of test vector leakage assessment. Remember we talked about leakage assessment of this implementation, and then find the vulnerable modules, and then kind of try to reduce their leakage, information leakage and all that. So there are a lot of effort. This area is kind of new, 2 to 3 years old or 4 years old. This might be a good area to get in. So now that I am done with post quantum cryptography, I am going to move on to quantum devices itself. What are the security problems do we have? And so the most of the problem on exact this space is by Professor Yakub Shafer. So he was in Yale University, I believe he moved to Northwestern or Northeastern, but most of his work by Yakub Shafer, and you want to look at that. But I want to just highlight 1 or 2 problems that people looked at. And in the post quantum, in the quantum security, people look at the security of the microwave generator, as well as, let me skip this, you already know, people also look at the quantum computer itself, what is going on in the quantum computer. Remember, we do not have physical access to the quantum computer. So somebody trying to attack has to do something like the attack we talked about, like cache timing attack. Somebody brings something there. So the analogy here is, when a victim kind of compute something, and then there is idle period, and then IBM, let us say it is IBM quantum computer, IBM does internal reset, and then the attacker wants to map the quantum circuit to the same qubits. Reset does not work completely. They are able to recover what was the computation done by the victim. So it was actually at that time that was actually a problem, that the reset was not big enough, not long enough to put it to the 0 state. Some residue was there, whatever alpha beta residue. Now I know this sounds silly, the things are so unreliable anyway. For normal mode, somebody stayed idle, somebody did reset, still you have enough information to break it. It does sound silly, but then again let us not do rational discussion with quantum computer. These researchers are able to figure it out. So that is basically state retention problem. And then, so these researchers have published lot more. I just wanted to explain 2 of them that conceptually can be explained. The second one is, let us say you have enough qubits in the machine, something like this. Let us say you have enough qubits in the machine, and let us say your quantum circuit you map to the, recall how do we work? Qubits are more like FPGA lookup table. You program them, you send pulse, you say these from now on these 2 guys are married, that is entanglement. These 2 guys should not talk to each other, that is kind of whatever, you put a gate and you block, you make them talk, you form gate basically, and all you do by sending pulses. Those qubits are physically sitting in the same place. You can do swap gate, and there are all these complexities, but let us say one of the program is running on this. Normally that is not how it works, normally it works mostly this way. Let us say you have 4 qubit, one quantum circuit is running on these 2, another running on these 2. So the top one could be the victim's quantum circuit running, the bottom one could be attacker circuit running. Then there could be a crosstalk like behavior. So this qubit might be able to figure out what is in this qubit. Of course, ideally this attacker, if this is the attacker would try to do an entanglement with that, but the design itself might prohibit it. So basically whatever kind of influence you get, That is the crosstalk, and the crosstalk is also a known phenomena in classical domain, and the phenomena is something like you are sending a 1 here and here is a line 0 here. This could be a bus between processor and memory. The crosstalk thing, if these lines are very thin, they are very close. So, if this line is 1, this line is 0, think of a capacitance, this will kind of, this capacitance is supposed to be empty, but this capacitance will charge, and this might be more than 0. If it crosses above the threshold, suddenly this 0 will become 1. Converse is also possible. If this 1 is a weak one, capacitance is just barely above the threshold, this 0 will try to pull it down, and if it just goes below the threshold wherever it is measured, then 1 will become 0. So, crosstalk is not a new idea. In fact, crosstalk problems in nanometer regime is actually more, and anybody who does layout or below, they will talk about it. That is all they do all their life, parasitic and crosstalk. So, crosstalk kind of behavior the researchers utilized to kind of figure out what is the information that victim is computing. And again there are mitigation techniques. There are a lot of mitigation technique like in secure reset, and this I talked about. There are techniques that how many times you need to reset, or the reset operation. Think of reset, remember those qubits does not know anything, you send electrical pulses, they get oriented in a certain way, right. You give a chocolate to a kid, they behave differently, but once the chocolate is over, the kid starts behaving exactly the same way. So, therefore, the reset, maybe how many times you have to reset and all that, there are mitigation techniques people talked about, that reset that guarantees that the state is actually gone, and so there are also work on how do you mitigate this problem. There are other ways of mitigating. If you recall, we introduced the idea of quantum steering. How do you use quantum steering to kind of mitigate some of these insecure reset? And this one we talked about crosstalk, and crosstalk also kind of behavior you can kind of mitigate through good compilation technique. You can do good compilation technique. I did not get enough time to talk about many of the classical compilation optimization problems still applies here, because even classical compilation you are trying to make area small, power small, performance faster and all that is the same thing. But here in addition we have one more parameter, reliability. Do I have to run these electrical pulses once, can I get the result, or I have to run it 10 times? How do I run minimum number of times and still get accurate, the fidelity of the things, that is the compiler's objective. So, now that we have little bit of time, I am going to talk about, before I conclude, the application specific security. All the security problems and primitives we talked about in classical and quantum domain, it is applicable to any domain. But when you look at in a specific domain, the security problems or applications or solutions are different. So, I can talk about many domains, but I am going to talk about 1 or 2 depending on the time. So, I want to start with the car, right. So, throwing a car out of the road without you being there is kind of trivial. Anybody knows why? Anybody's car can be thrown into ditch, whether you violate a law out of it, I do not know. Anybody knows why this is possible? I can sit here, you are driving, crossing the bridge in the Brahmaputra, I can take your car turn any way I want. Why is it so easy? Anybody can do it, even Om can do it. How is it possible? Because there is an inherent story to this car. A car basically lives, or the car design lives somewhere around 30 to 40 years. You may not feel that way, let me elaborate. When a car gets designed, or the blueprint, or the whatever the paper, when you design, you have the design in the paper, and when it is on the road, it is 30 to 40 years. I am not talking about the exotic cars people maintain and vintage cars, I am not talking about regular cars. Because the thing is, when it is in the paper, depending on which country it is designed, they have their laws, they have to get it approved. That would take you somewhere around 2 to 5 years to get approved, whether there is a seat belt law or whatever law it is. Then once you have that, you design and dealer and sell, that you are looking at 1 to 2 years time span. When you buy, most people even in the rich countries, they drive 5 to 10 years, and then that car does not go to the dustbin, somebody else buy, continues. So, think about a security mechanism that was built 20, 30, 40 years ago. Even a baby who is not born can break it. So, the part that is even worse in automotive system, automotive standard does not allow any security verification and checking, which I will explain in a moment. So, couple of things happened. One, I am saying security built in 20-30 years ago is not going to work, and it actually should not be a surprise. 20-30 years ago nobody used to talk about security. So, all the buses, the bus protocol where all the components, embedded devices are connected, they have no built in security mechanism, none at all, right. So, if you recall, we talked about reconfigurable security. If it was implemented in that, you can take it to a dealer, and if you want to pay, they might upgrade, but it is not even designed that way, right. There are a lot of bus configurations over the years that were built, and now these days whatever bus configuration they are developing, they have security in mind. But in same analogy applies 20-30 years later, if it is not upgradable, modifiable, it would look like a joke, anybody can break it. So, that is why when I come to India, I go home always with this one. This may break, doors may fall, it has no electronics, and production stopped sometime in 2014, but it still works. In Kharagpur you still have in abundance of those. And but any other car, depending on when you bought and how much money you paid, it has tons of electronics, doing tons of sensing, actuation. Remember when I talked about firmware security, it has a lot of electronics and lot of vulnerabilities, lot of points of attack. And in fact, most of the attack in the first page I showed, they try to attack the infotainment system, even the advanced car infotainment system, where you have all these. Early days you used to have CD player, these days I do not know what you have, those are not secure. So, people get access to the infotainment system, then they get access to the engine control system, and then they make the attack. To make matters worse, all these so called smart cars like smartphones are really unsmart, they have machine learning in it. This is the first time I am talking negative about machine learning. So, because you have the machine learning in there, machine learning model, and they are trained, and then anything happening, wrong decision is making, information is flying to the cloud. At the end of the day, when you are doing charger or it is resting, the machine learning model from the cloud is basically updating to the new machine learning model. Maybe the observation of your car, maybe many other cars reported, the machine learning in the cloud got retrained based on that, and it comes a model. So, vulnerability here, vulnerability in communication, vulnerability in cloud, tons of vulnerability you are carrying with. If that is not enough, then machine learning, the autonomous car or community has no notion of security verification. They have something called ISO 26262, safety verification. So, even if you are driving a car and suddenly you feel the sky is going to fall on top of you, the car, autonomous cars, when you do not have a control, they are not going to stop. They will do something called graceful stopping. The car will, in your computer something looks wrong, ransomware, you press the power button and stop it. You cannot stop in the middle of the street, because it is a danger for the passenger. So, that is why safety verification problem is passenger's life is more important than China trying to hack a computer or Pakistan trying to hack a computer from your car. Nobody cares. So, passenger's life or safety is paramount. That is basically the functional safety, and that is the verification, that is the guarantee everybody worried about. So, in this domain everybody has a different focus altogether. Now, that is why I have this long life for automobiles actually makes it so easy, even a caveman and cavewoman can break it. Ohm can break it faster than them. Now, it is time to conclude. I want to show you two perspectives from different people, but before I show that, I want to kind of recap that we started with the story, today's security is not enough, and what are the vulnerability. We kind of looked at the landscape of vulnerability. I kind of talked about, if you want to start research, start here. So, where you have all the vulnerabilities and attacks known as of today, and it should not be surprising then we kind of know everything. What are the attack goal, what attacks are possible, what are the countermeasures, and it is a cat and mouse game, whether in hardware, firmware, software. Attacker also know you have this mitigation, they will come up with better attack, better kind of attacks, and you try to mitigate. So, it is kind of going to go forever in every domain. If that problem is not enough, if you kind of put other conflicting requirements, I want to pull in just two examples. One is security and debug. Security should be clear, we talked about security for 10 days. We are trying to stop, pause the vulnerability. Debug problem is, think of the engineers in the company, test and verification engineer, their objective is to just to verify the design. So, what does debugger want? Debugger want the full visibility of everything, software, hardware, firmware. If I can do printf of every variable, that would be ideal. But the security engineer says no, do not come close to the variable named key, do not even come 1 million radius from key, not even this variable x, because if you know x, you will be able to infer y. Security community does not want to have any visibility, zero visibility. Verification community want full visibility. This is a constant fight in every company. Anybody knows how this fight is resolved? Because security people cannot win, because if you do not let me touch anything, how on the earth am I supposed to verify your security module? Forget about my functionality of the rest of the design. How do I verify your security module will encrypt correctly, key will travel correctly? How would I verify all of that? The way it resolved is that, remember, debugging we still have trace buffer and all that post silicon, we still have those notion of the tracing or trace buffer. It is just that trace buffer is not allowed to have any variable which are security or sensitive variable, not even variable that through contact tracing or observability tracing you can observe. Now, that still does not solve the problem how the security engineer will the verification engineer will verify. During design time, it has full visibility or some form of visibility. When you sell it, you kind of lock and block it. That is why when you have a design, you send it to your company, and sometimes your friend get a refurbished version of it, you get a new version of it. That is the catch. If the problem is in the security area, they triage and find it, they will not be able to debug any further. So, they give you a new device. But if the problem is in the other area, they will just fix it, do firmware patching, do something, and then give your own phone back when they can fix it. But whatever it is, this conflict is not going to go away anytime soon. So, security problems are going to remain relevant. One last thing I want to talk about, security and reliability conflict. So, I worked extensively on the pacemaker, neurostimulator and all those for a long time, and I got interested. I went to go to a neurosurgeon, and they were digging literally holes on the top of a brain, and I am like curious, what are you doing? It is like, it reminded me, you know, this oil exploration, they dig hole here, dig hole there to see if you have petrol, diesel, whatever, I do not know what they extract. So, they try to find where, which one?
They extract petroleum.
Petroleum. They extract petroleum wherever it is. It is as if the brain, and I am like, I literally asked the neurosurgeon, his brain would be damaged. He said, oh, these guys' brains are damaged. So, I am talking about countries where people live 80, 90, 100 and more, and many of them has dementia, whatever, Alzheimer and all kind of diseases. So, the objective is you put a stimulator, and then it will generate pulses in the range of hertz, not megahertz, not gigahertz, brain operates in the hertz level. So, in the hertz, and if you do in right place in thalassemia, right place in the brain, then you might be able to move your right hand, left hand and all that stuff. And now, the same thing in the pacemaker. Pacemaker, basically there is one nerve that basically comes in an ventricle. So, it tells the ventricle to pump, so that blood goes to the thing, and if that pulse does not come, it does not pump. So, that is why it artificially generates that pulse every, I do not remember, 16 millisecond or whatever, it generates that pulse. It monitors, did the pulse arrive? If it does not arrive, then it generates a pulse. So, all of this is perfect, but the problem is the attacks, basically Kevin Fu's group basically showed that you could have a $20 kind of apparatus and make anybody die and you will not go to jail. How does that work? Because these devices have transmitters, and when you send the signal, it becomes on, starts receiving, otherwise transmitter stays down. And why that mechanism was there? Because in early days before 1990s, anytime you want to put a pacemaker or you want to put any of those, you have to do operation again, take it out and replace it. If battery is not working, something went wrong, people thought, Why do you want to do that? Most of the time things are fine, some settings need to be changed. So that wirelessly doctor can change the settings, that is when those stuffs are in. And now anytime you put a technology, people did not realize what will happen, and then some researcher came up with the idea, I can turn on and turn off the transmitter million time in few seconds, your battery is down and you are dead. At that time there was no law, this is not a secondary murder, not a second degree murder, but anyway whatever that is, and at that time US Vice President basically Dick Cheney took out the because of that got freaked, everybody got freaked out. It is like post quantum cryptography. When you hear this, oh I am sitting there somebody playing something video game and I am dead, they just took I would rather die from arrhythmia than just somebody making an attack. But anyway all this story I do not want to go further detail. What I want to talk about, question is why did not they put encryption in it, why anybody with any signal can communicate. It should be only the device given to the customer or the patient or the doctor, and that should have this all the authentication encryption we talked about. Any thoughts why it did not have any of those?
The same card technology happened here.
No, encryption authentication is known for a long time. These stuffs and these are all in hardware for a long time. So, building this into this device is not a problem.
Sir, could you please repeat the question once more?
Why authentication encryption was not built in? Anybody can buy any device, keep sending signal, ideally it should not accept those signal, right? Yes please.
The cost and second is resource use. If we are going to implement encryption in those sensitive device, it will have resource impact also, and cost will be increased twice or thrice.
Right. So, you are on the right line. If you because I am going to say something you won't believe. The people who get most paid in any country is heart surgeon and neurosurgeon, and they are the most idiots. So, when I started talking, this guy is referring this thing as a battery. I am like, on earth why are you calling it battery? Then I started talking to so many people, every doctor refers to this as a battery, because 98% of it is battery. But for people in computer science or electronics or electrical, we see it as electronics. It did not occur until then that electronics is less than 1 or 2% of the story here. For everybody else it is a battery. They did not even thought it is needed to be controlled, preserved, there is no stuff. Even doctors do not know. I asked them these companies like Medtronics do not sell these devices, only doctors and hospitals can buy them. So, then how do I do research? I asked this guy and he gave me a bag full of things with blood in it. I said, what am I going to do with this? Oh, there is enough battery life left, 1 or 2 years you can do research. Then my dean said, you can't use it, your lab is not biologically certified. Then the medical people also pushed back, the doctor is not supposed to give that to me because this has personally identifiable information. That is when he started saying this is a battery, and then it occurred to me. Anyway, so the thing is, we always see things from our side, you have to look at people from other side, the people who are designing, the people who are using, they think it is a battery, and because it is a battery, so then battery life is the primary objective for everybody. Putting encryption will cost around 30%. So, typical battery like this lasts about 8 to 10 years. Now, if you put an encryption, it would reduce by 3. So, if I put it on myself, every 7 years I have to change it versus every 10 years. So, that is basically the deal, that is one, but that is not the reason why people did not put in. What do you think else is the reason? The reason is, if it has an encryption, it has a key. Who knows the key? It is only me. If I go to a country, choose your country, the least favorite of yours, Pakistan, right. So, if I go to Pakistan, something happens to me, of course, first thing you will say, why the hell you going to Pakistan in the first place, and the doctor gets to me, I can't talk, and by the time they try to connect a consulate and go to the country, home country, and find the key, I am dead. So, my reliability problem or the security problems, my reliability problem. So, there are many such things we do not think about, and we just pass comment, oh, they should have just did this or that. Now, these days some variation of encryption is actually in place, there are some mechanism, that is why the medical thing, this approval process takes so long, there are different checks and balances. But nonetheless, I wanted to just give you idea that security, whatever you learned, when you try to apply in different domain, You have to understand that domain's sentiment. You do not want to hurt anybody's emotions. With that, I basically want to conclude. So, basically in this whole course we talked about there are wide variety of security vulnerabilities, and we kind of talked about AI or explainable AI is very promising, and I hope you actually learned and you will use it for your work. Thank you. Now, no more recording off. So, I am going to tell you something that I enjoyed. So, I started coming from 2017, and then about 2024 I got an email from a lady, and she said, please do not delete my email before reading all of it. Nobody normally writes like that. I read through, and she said, can you review the PhD thesis of my student? Normally I delete it. And then I said, this is basically I attended one of your workshop, I learned about hardware Trojan, this is my first PhD student, and this is his PhD thesis. I was like overwhelmed with that. And so, that is actually right way of learning. You learn something, you use it, you do not have to come back with a PhD student with that topic, but it is a little more interesting than that. After that day I went to the guest house, and there was a guy of his age, no, a little older, about 11-12 year old, and he asked me, do you know where my mom is? I am looking left, looking right, it is a IIT dude, it is like 10,000, 20,000 people, I do not know you, how the hell am I supposed to know who is your mom? I did not say anything like that. I basically asked, do you know where your mom is? Oh, there is some course on by something. Then I know it is my course. Then I said, I came by car, and she is walking, she will be here 10-15 minutes. And story is even worse than that. The day we joined, Dr. John sir said, oh, I had to come to your guest house. I said, why? Now, guest house will not keep in the same room a guy and a girl. So, this lady came to think this is his son, guest house has rules, the guy and girl should know, the John sir has to come, this is mom, this is kid, please allow. Anyway, long story short, I gave you lot of information not relevant. The relevant part is this lady actually took and understood, she did not know anything about security, took and understood, then went back, did research, and I evaluated the PhD thesis. That is kind of like nice movies, nice ending, it does not have to be, but you make use of it. Otherwise, it is a wastage of your time and my time. Thank you.
So let us give a big round of applause to Professor Mishra. So his energy level always inspired me at least, and I hope it inspired you as well. He is 53, but he always behave like 23, right? He's always, you ask him to go to my lab, ask to discuss some research, he will always agree, right? So he's a very, very energetic person, and if you are working in this domain in future, and if you are getting trouble, feel free to contact sir, and I'm sure he will help you in technically and in other way also. Okay, so we are done with the technical session. No more technical discussions for rest of the day. We'll enjoy our food and we'll come back, give the exam, the small part of it, and then we'll interact with you more, right? So 10 days we only talk, right? You are not allowed to talk that much, right? Only ask questions. So today you will talk and we'll listen, okay? Post lunch. Thank you.
And we will not ask any questions.
Okay, so we'll have lunch now. 1:30, please join me.